So in this video, we talk about quadratic variation of a standard process. So what we will prove is that the sum of squares of increment of such a process always converges to the integral from 0 to t of bs squared ds. And that will be the missing element in our proof of 511, so the generalized version of Ito integral for a process xt that you can also think of as a stochastic version of the chain rule, right? The proof of this is exactly like the proof of Ito's formula, except you have to understand how this term, this correction term, arises, and it arises exactly as in the proof of Ito formula from the limit of this sum of increments squared. In the case of the Brownian, it was tending to t, and notice that t is the integral from 0 to t of 1. But more generally, the term that you get here involves the integral from 0 to t, not just of 1, but of b of s squared. Now, this convergence is going to be a convergence in probability, and it's going to be a convergence for any choice of partition of the interval 0t. So the first thing we need to do is formalize that a little bit. Now, a partition of the interval 0t is just, as always, a increasing sequence of points ti, such that at time at I equals 0 you are at 0, and at the end point t capital N you are at your end point of your interval t. Now, given a partition, there's something we call the mesh of the partition, which is the maximum of the distance between ti minus 1 and ti. So when we refine a partition, when we take this limit as n goes to infinity, really we're asking for the mesh of the partition to tend to 0. So what we're going to call the quadratic variation of a process. So first of all, we can talk about a quadratic variation of a process associated with a given partition. So we call that the p quadratic variation of the process. You give me a partition and I can form the sum of the square of the increments over that partition, right? That's for a fixed partition, and we call that the quadratic variation associated with that partition, or the p quadratic variation, where p is the partition. Now, imagine that as you refine the partition, that is to say, you take any sequence of partition which mesh size goes to 0, then the corresponding sequence of random variables that you obtain to this finite sum converges in probability to something, right? If that thing exists as a limit in probability of a sequence of p quadratic variation when the mesh of p goes to 0, then you say that z of t admits a quadratic, that x of t admits a quadratic variation process, and this quadratic variation process is z of t. And the notation for the quadratic variation of the process x is, bracket around x subscript t would be that process at time t. And this is the process zt that you obtain as the limit in probability of the sequences if this limit exists, and of course is independent of the choice of partitions that you use to approximate zt. Now, the theorem we want to prove, this definition is a bit complicated, just like the definition of the Riemann integral, because you want something for every partition and every refinement. But the point is that in theorem 5.15, we will prove that any standard process does have a well-defined quadratic variation, and the quadratic variation is, well, what we said it would be in our version of the stochastic chain rule, namely the integral from 0 to t of b squared. So in proving the theorem, we'll have two things to do. So, notice that the quadratic variation doesn't depend on a. So first of all, we should see that if b is 0, right, if you don't have this term, then the quadratic variation of a process which satisfies an equation of the form dxt equal a dt should really be 0. And that's what we're going to prove in Lemma 5.16. So if you just have a process that has purely a dt part, no dbt part, then this process does have a quadratic variation, but this quadratic variation is 0. And that's the way to recover the standard chain rule, the standard fundamental theorem of calculus, right? You don't get any correction term in the standard theorem of fundamental theorem of calculus, That's literally because if I have a function, then you can see it as a standard process with A being deterministic and B being 0. And if B is 0, then the quadratic variation is 0. So there is no correction term, as in Ito formula, in the deterministic version of the fundamental theorem of calculus. So we're going to prove that first, that the A contributes nothing, and then we're going to build up to understanding what is the contribution of the B. So let's prove lemma 5.16 first. Okay, so I have my process, and it's defined by a omega t equal the integral from 0 to t of little a omega s ds. Now, and that's for all t, let's say in an interval 0 to capital T. Now, if I form the set, let's call that E to be the set of all those omegas such that the integral from 0 to t of absolute value of omega s ds is finite, then we know that this set needs to have probability 1. This is part of the definition of being a standard process. So what can I say? If I have something that has a finite integral like this, then I can also say that for every omega in E, the map little t goes to integral from 0 to little t of a omega s ds is continuous, and it's continuous on a compact set, so it's uniformly continuous. Okay. Now, if it's uniformly continuous, that means that for every epsilon, there exists a delta, such that for every p a partition, let's say, of 0t, that's your little t, and for every, so p is going to be a set of tj's, j's running between 0 and n, and for every j between 0 and n minus 1, then whenever tj plus 1 minus tj is smaller than delta, then the integral from tj to tj plus 1 of a omega s ds, that's for every omega in E, is certainly smaller than epsilon, right? This is because of the uniform continuity of that map. So if you have your partition such that the mesh size is smaller than delta, then this will always happen. So what we have, in other words, is that for every omega in E and for every epsilon, there exists a delta such that for every p partition, again p being a family of tj's, if the mesh size of p is smaller than delta, then the maximum over all j's of the integral from tj to tj plus 1 of a omega s ds has to be smaller than epsilon. But what does that tell me about the p quadratic variation? So this tells me that for every omega in E, for every epsilon, there exists a delta, such that for every p partition, when the mesh size is smaller than delta, then QP, what is QP? It is the sum j equal 1 to n of the integral from 0 to tj of a omega s ds minus the integral from 0 to tj minus 1 of a omega s ds, and then you square that. But that is equal to the sum j equal 1 to n of the integral, or smaller, of the integral from tj minus 1 to tj of a omega s, and then I could use ds, and then this is squared, but we know that these quantities are smaller than epsilon, so this is smaller than epsilon times the sum j equal 1 to n of the integral tj minus 1 to tj of a omega s, and then this sums up to being the integral from 0 to little t, which is certainly smaller than the integral from 0 to capital T of a omega s ds. Okay, so what have we got here? We've got that for every epsilon, if the mesh size of the partition is small enough, then QP is smaller than a multiple of epsilon. Therefore, for every omega in E and for every Pn partitions, if mu of Pn tends to 0, then QPn, that's QP of omega, and QPn tends to 0. So what we have is for every partition, when the step size go to 0, QPn goes to 0 almost surely, because E has probability 1, and that is even stronger than having the convergence in probability. Okay, so the next step in the proof, now that we've seen that A doesn't contribute anything to the quadratic variation, in order to understand the contribution of B, we need to prove a fairly technical lemma. So this technical lemma is about general continuous martingales that are uniformly bounded. Okay, so for those one, we'll see that the P quadratic variation can be estimated by the expectation of the continuous martingale somewhere at the endpoint of the time interval. That's essentially a consequence of the martingale property, something reminiscent of the L2 maximal inequalities of Doob. So we're going to prove that concrete estimate first, and then using that concrete estimate, we're going to see that, well, if you were to look at a fourth power version of the quadratic variation, so raising the increments to the fourth, then such a thing, like not a quadratic variation, but a power 4 variation, would always go to 0 as you refine the mesh side. And that's going to be also critical in our proof of the existence of the quadratic variation for a general standard process. This is a fairly technical lemma that sort of beautifully exploit the martingale property. So let's have a look at how the proof goes. So, okay, so I'm going to give myself a partition. So it's a family of tj's, j between 0 and n. And then just for the sake of notation, I'm going to denote by dj the difference between z of tj and z of tj minus 1 for all j between 1 and n. And then I'm going to start computing the L2 norm of QPZ squared. Now, what is that? Well, it is the expectation of the sum j equal 1 to capital N of z tj minus ztj minus 1, which is dj, and you square that, and it's an L2 norm squared, so you square that again. So let's expand this thing into a double sum, and we're going to have one term, which is the term, the diagonal term, where you get an expectation of dj to the 4, and that's the term that we will see goes to 0. And then we have another term, which is the sum j equal 1 to n, sum for, well, let's call that I, and let's call that j, running from I plus 1 to n of the j squared di squared. Take an expectation of that. This is the sum where I is not equal to j and j is bigger than I. You've got the same sum with the role of I and j reversed, so you get this thing twice. Right, so let's compute a bit this expectation, this second expectation here. As always, I can condition on whatever I want, and that's not going to change the expectation. So I'm going to take, so I've got this sum I equal 1 to n, the sum j equal I plus 1 to n, and I'm going to take the expectation of the expectation, conditional expectation of di squared dj squared, and I'm going to condition on ftI. Right, now j is above I, as at least I plus 1, so it may not be FTI measurable. Di square, on the other hand, is FTI measurable. So the point of that is that I get to sum I equal 1 to n, sum j equal I plus 1 to n of the expectation of di squared times the conditional expectation of dj squared given FTI. Right, now I want to show that this somehow simplifies, and the reason why it simplifies is the following consequence of the Martingale property. So what happens when I look at the expectation of the sum j equal I plus 1 to n of the dj squared conditioning on FTI? Now I claim that this is actually equal to, that's a claim, we're going to need to prove it, the expectation of the sum of the dj and then squared that. So I claim that all of the cross term here would be 0. Let's call that claim 1, given FTI, and then this is a telescoping sum, and the whole thing becomes the conditional expectation of z capital T minus z t I plus 1, that's minus 1, so minus z t I, all of that squared given f t I. Right. And that, by the way, you would be able to control by 2, so 4 times the supremum of z t infinity, of z little t infinity, because both z capital T and z ti would be smaller than this, and then you have a difference of the two, and so you would get something smaller than 4 times this supremum. Okay, now this would be helpful. This will allow me to conclude my argument here in star, but I need to prove claim 1. So claim 1 holds because if I have a j and a k that are between I plus 1 and n, and let's say that k is greater than j, then what happens when I take the expectation of dj dk given FTI is the following. I get the expectation of z tj, by definition, minus z tj minus 1 times z tk minus z tk minus 1. That's all of that given FTI. And I could just use the tower property and condition on ftk minus 1 first, because ftk minus 1 would still certainly be above ti. So this would be the conditional expectation of ztj minus ztj minus 1 times ztk minus ztk minus 1, and then condition that on ftk minus 1, and all of that is condition on FTI. And now if what you then say, because k is greater than j, this may not be ftk minus 1 measurable, but it certainly is. So what you're getting is the expectation of ztj minus ztj minus 1 times the conditional expectation of ztk minus ztk minus 1 given ftk minus 1, and then all of that condition on FTI. And this is 0 because zt is a martingale. So the cross term of that form here in this double sum, when you expand that square, are all 0, and that's why this expectation of the sum square is actually the expectation of the sum of the squares, because all of the cross terms are 0. So this gives me this very nifty technical estimate on this part here of my computation. And now, putting these things together, what do I get? I get that my QPZ in L2 norm squared is smaller than the sum j equal 1 to n of the expectation of dj to the 4 plus 8 times the sum I equal 1 to n of the expectation of di squared. Okay, now let's put these things together again. I could, oh sorry, and I forgot here the term, no I didn't, I forgot the supremum of zt infinity, which was squared here by the way. Supremum of zt infinity squared. Now I do the same thing for the dj4. I estimate dj squared by this supremum, and that gives me this supremum zt infinity squared, t between 0 and capital T, times, okay, I get it one time here. Oh no, actually there's two times this supremum and its square, so I get it 4 times from here and 8 times from there, so altogether 12 times, and then that's that times the sum of the expectation of dj squared, j running between 1 and n. But then again, I've got a martingale, so the difference of the martingales are orthogonal to each other. So this thing here is 12 times this sup times the expectation of the sum of the dj's, all of that squared, because all of the cross terms again disappear using the martingale property. And so this sum telescopes, and I get 12 times the supremum zt infinity squared times the expectation of zt minus z naught squared. And that is 1. So 1 is proven, that is 1, and this is the constant c that appears in 1. 12 times the supremum of the sup norm of the process squared. Okay, so to prove point 2, we have to remember that zt is not just a martingale, it's a continuous martingale. So there exists an E in sigma that has probability 1 such that t goes to zt of omega is continuous for all omegas in E. And because it's continuous on a compact set, it has to be uniformly continuous. Now that is to say that if I define, let's say p delta omega to be the maximum of z, actually that's not right of the omega, let's just think of that as a random variable, maximum of zt minus zs whenever t minus s is smaller than delta, this quantity goes to 0 at a point omega, as delta goes to 0 for every omega in E. So P delta goes to 0 almost surely as delta goes to 0. Okay, so now we have a partition, and let's say that its mesh size is delta. So delta is going to be by definition the mesh size of our partition. What can I say about the expectation of sum of dj to the 4? Right, as j runs between 1 and n. So I can certainly say if the mesh size is delta, that this is smaller than the expectation of the sum j equal 1 to n of p of delta, right, squared, times dj squared, because an increment will have to be smaller than p of delta, because delta is the maximum size of an increment between a tj and a tj minus 1, which is smaller than delta in distance, because the mesh of the partition is delta. So what does that tell me? Well, that tells me that the expectation of the sum of the dj to the 4 is certainly smaller than, okay, what do I want to do now? I want to use Cauchy-Schwarz, and say that this is smaller than the expectation of p delta squared raised to the power 2, so 4 raised to the power 1/2 times the expectation of the sum of the dj squared squared. And this thing here is exactly the L2 norm squared of QPZ. So what I get here is the L2 norm of P delta squared, oh, and that's to the 1/2 times the L2 norm of QPZ. Okay, but we have this control for QPZ, so this entire thing is smaller than P delta squared in L2 norm times the 12 times the supremum of the ZT infinity raised to the power 2, and then times the expectation of ZT minus Z naught squared, and all of this has to be raised to the power 1/2. This doesn't really matter because all of that is a number that is independent of the partition. So as you send the mesh size of the partition to 0, P delta goes to 0, almost surely. And then P delta is also certainly smaller than 2 times the supremum of the ZT. So by dominated convergence, we have that P delta squared in L2 norm goes to 0 as delta go to 0. And this means that we have one term here, which is just a finite number independent of P and therefore independent of delta, and here a number that goes to 0 as delta goes to infinity. So as you refine your partition and you make the mesh size go to 0, these quantities here will go to 0. And that concludes the proof of this particularly technical lemma, but we'll see that these estimates are exactly what we need in the proof of the existence of quadratic variation for our standard process. And we'll do it next in the special case where a is equal to 0, and then we'll put everything back together. Okay, so we have one last lemma to prove before we can have our theorem about the existence of quadratic variation for any standard process. Now, we consider in this lemma the case where there is no a, so dzt is just bdbt for some b in L2 log, and we're going to make one extra assumption that we'll remove eventually, and that is that the sup over time of the sup norm over the probability space of the integral of bs square is finite, and that finite number we'll call capital C. And under this extra assumption, and with little a being 0, we'll prove our result. So this is a special case of our result, and then we'll remove the extra assumption and put the a part and the b part together in the proof of the theorem after that. So let's prove this case first. This is almost what we want, and this would use our technical lemma 5.17 quite extensively. So let's give ourselves a partition. Okay, and let's define dj. So this will be the sort of quantities that we're interested in, the sort of differences we're interested in, but they will involve, contrary to what we often do, the ztj minus ztj minus 1 squared, and then minus what we need to compensate for. So the tj minus 1 to tj b dot s squared ds. So we're going to look at those quantities, and I claim that these quantities have a orthogonality property, just like Martingale differences do. So in order to see that, if I take a k that's greater than j, okay, but still smaller than n, and this is greater than, I need that greater than 1 or equal to, then when I take the expectation of dk dj, what do I get? Well, I get that this expectation is the same as the conditional expectation, dk dj, and I could condition on ftj itself, actually, And then what would that give me? Well, k is above j, but dj is ftj measurable. So what I'm going to get here is the expectation of dj times the conditional expectation of dk given ftj. And I'm claiming that this is going to be 0. Now, why is that? Because the expectation of dk given ftj is what? So it is the conditional expectation of the integral between tk minus 1 and tk of my bs dbs, and this gets squared and condition on ftj, and then you subtract from that the conditional expectation of the integral from tk minus 1 to tk of bs squared ds given ftj. And right, if I were not conditioning, then the fact that this is 0 would just be Ito isometry. But here, what I get is that it is 0 using the conditional version of Ito isometry. And I'm going to leave proving that as an exercise. You use the proof of Ito isometry and use the proof that k is greater than j, and you realize that you could condition on ftj in the proof of Ito isometry here. And because you're integrating on an interval that is above j, that's important in the proof. So do that exercise, prove that conditional version of Ito isometry, and that says that this is 0, but this works with the same proof as Ito isometry in that case. That doesn't mean that you can condition on anything you want and still get an Ito isometry, right? It's very important that we are integrating here on an interval that is after tj. If not, we wouldn't get a conditional version of Ito isometry. Okay, so how do we use this? We want to compute the L2 norm of QPZ minus integral from 0 to t of bs squared ds, maybe square that, and this is the sum of the dj's, which telescopes to give exactly what I want, from 1 to n, and in L2, n squared. So this is an expectation of this sum of dj, and all of that is squared. But by orthogonality that we've proven just before, this double sum collapses to a single sum, and I get the sum of the expectation of the dj squared. Now the dj themselves are a difference of two terms, and you should realize that when you have a difference of two numbers, a and b in R, and you square that, well, this is a squared plus b squared minus 2ab, and minus 2ab is certainly smaller than 2 times a squared plus b squared. That's because a squared, actually it's smaller than a squared plus b squared itself. That's because a squared plus b squared plus or minus 2ab is a square itself, so it has to be non-negative. So this entire thing is smaller than 2a squared plus 2b squared for sure. So what I have here is smaller than twice the sum j equal 1 to n of the expectation of ztj minus ztj minus 1 to the power 4, plus twice the sum j equal 1 to n of the expectation of the integral tj minus 1 to tj of bs squared ds, and that is being squared. Okay, now notice that the first term of this sum here tends to 0 as the mesh size goes to 0. That's by Lemma 5.17. Right, we now have a fourth power, and we've seen that as you refine the mesh size, this has to go to 0. Now, what about this term here? We still need to show that this term goes to 0, in probability at least, as you refine the mesh size. So let's do that now. Okay, so for that last term, the argument is a bit similar to what we've done when we've treated the case where dzt was just of the form a times dt. So what happens here is that the integral from 0 to t, little t, if I look at the map that sends t to this integral of bs squared, because bs squared is Lebesgue integrable, let's write that as an omega. So for almost every omega, I have continuity of this map and therefore uniform continuity on the compact interval 0 to capital T. So if I define the quantity, let's call it rho delta, to be the supremum of the integral from t to t prime of bs squared ds, over all t and t prime, such that t minus t prime is smaller than delta, then this quantity has to, which is a random variable because bs is a process, has to go to 0 as delta goes to 0 almost surely. Okay, but then what can I say about the sum j equal to 1 to n of the expectation of the integral tj minus 1 to tj of bs squared ds, all of that squared? Same trick as before, I could control that by rho of the mesh size of p times the expectation of the integral from 0 to capital T of bs squared ds. And we know that this is finite, and therefore this has to go to 0 almost surely. So what am I doing here? Yeah, I cannot quite do that because of course this would depend on omega. My rho of delta is itself a random variable, but what I can do is I can do that for every omega. So for almost every omega, this is controlled by this times this quantity. And that's where my extra assumption really comes in. So it's very good that I made that mistake. Then you really see the point of the extra assumption. And this is really a random variable at a point omega. This is a random variable too, but this is controlled by c, which is a constant, another random variable. I take a supremum over omega here times rho of mu p of omega. That's for almost every omega. So now what does that tell me? That tells me that sum j equal 1 to n of integral tj minus 1 to tj of b of omega s squared ds squared, I forgot to square that, so if I square that, I pick that, that thing here has to be, so I control one of them by the rho, and then the other one, the sum, gives me this. So the entire sum of this squared is going to 0 as mu p go to 0 almost surely. This is happening almost surely, but in the meantime, I also have that sum j equal 1 and integral from tj minus 1 to tj of b of dot s squared ds, and all of that squared is certainly controlled by c squared, right? Because I can control any one of these by c almost surely, and then the entire sum can also be controlled by c. So this is smaller than c squared almost surely, and so dominated convergence concludes the proof, because I have almost sure convergence of that term to 0, and so it's expectation that I wanted to control here does go to 0 too, because the thing that I'm taking the expectation of is controlled by, well, by a constant, so by an element of L infinity, therefore it's controlled by a fixed element of L1. Okay, and that concludes the proof of that other fairly technical lemma, which proves that every standard process that doesn't have an A part and under an extra quantitative assumption on B about the sup norm being controlled by the C here does have a quadratic variation, with the quadratic variation being what we want it to be. Right, now the last thing we need to do is put all of these lemma together and prove our theorem. Okay, so now we prove our theorem in the general case where dxt is a dt plus b dbt. Now, in our lemma, we had an extra quantitative condition. So in order to apply the lemma with this extra information, I introduce a sequence of stopping time, Tm, for m in n, defined as the infimum of those t's, such that the integral of as before the stopping time, the integral of as ds is not too large, so let's say it gets above m after that stopping time. The integral of b squared is not too large, it's above m after that, and I also need the integral of bs dbs squared, no, not squared, the integral of bs dbs in sup norm to be not too large, so it gets above m after that. Right, so you take this stopping time, all this condition satisfied. Again, we have inverse images of measurable set by something that is ft measurable, so we do get a stopping time in that way. And now we have fixed p a partition. And the idea is that up to that stopping time, I can apply my lemmas. So if I look at the p quadratic variation of my process stopped at the stopping time, okay, well, it is the quadratic variation, the p quadratic variation of the sum of two processes, one being this integral of as ds, and the other one being the integral from 0 to t of bs dbs. I know how to handle both independently, but unfortunately the quadratic variation is a sum of squares, so you know, it's not linear. But okay, but I can expand the squares and I would get that this is equal to the p's quadratic variation of this process, sorry, no squared, this process plus the p's quadratic variation of that other process. Oh, and of course I need to stop that at tau m, and here I need to also stop that at tau m. And we know that this is the same thing as stopping the process here before tau m, stopping the process here before tau m, thanks to our uniqueness theory. Well, actually here it's not even uniqueness, you know, it's just linearity of the Riemann integral, but here it's uniqueness of the uniqueness result up to stopping time of the Ito integral. And then we have a cross term which is twice the sum j equal 1 to n of the integral tj minus 1 to tj of as times this indicator function, that's ds, and then times the increment here, tj minus 1 of tj bs before tau m, but this time dbs. Okay, now I know what happens to the first term. It goes to 0 as you refine the mesh side. I know what happens to the second term. It goes to the integral of bs squared up to the stopping time. And I really would like these terms to go to 0. And they do, because I can apply Cauchy-Schwarz inequality. And then I can say that this sum j equal 1 to n integral tj minus 1 to tj of as before the stopping time ds times the integral tj minus 1 to tj of bs up to the stopping time dbs it's certainly smaller, almost surely, than the sum of these things here squared and the sum of these things squared. So this would be the quadratic variation. So the quadratic variation, t goes to integral from 0 to t of as times this indicator function ds raised to the 1/2 times the same thing from the bs part. But now the bs part, what we have here is finite, and what we have here is something that goes to 0 by the very first lemma we've proven. So by the lemmas 5.16 and 5.18, we get that the quadratic variation of t x t minimum tau m, as you refine the mesh size, so let's call it like that. If I have a set of partition and their mesh size goes to 0, then the family of quadratic variation as n goes to infinity will go to the integral from so the quadratic variation of this process over the full integral will go to the integral from 0 to capital T of b of s times the indicator function s below the stopping time, bs squared ds. Now that is almost what I want, but of course I still have this family of stopping time. But my capital M was arbitrary, and I eventually want to send it to infinity. So here is how you do it. So this convergence here, by the way, that we've seen in the lemma happens almost surely, or happens in probability. So what we do now to put all of these things together is that we give ourselves an epsilon and an epsilon prime, and then we pick m in n large enough such that the probability that tau m is smaller than capital T is smaller than epsilon prime. You can do that because the probability that the probability of the union of the sets tau m equal capital T is 1. So by taking m large enough, you can make it highly unlikely that the stopping time happens before the end of the time interval. And so once you have that, and that's why all these statements are in probability, you can look at the probability that qp n of x minus the integral from 0 to capital T of bs squared ds is greater than epsilon. And there's two possibilities: either your tau m is before capital T or it's not. And so if it's before, this has probability at most epsilon, and if it's after, then you're really looking at the probability that the process stopped at the appropriate stopping time minus this integral stopped at the appropriate stopping time. Right, I should do that for every little t actually. For every little t I need to pick my... No, I do that on the interval 0 capital T. So I do that on the interval 0 to capital T, and then I look at the process stopped at tau m, and again I use the uniqueness theorem to say that stopping the entire thing is integrating the stopped process, and this is minus bs squared ds has to be greater than epsilon. So this entire thing is smaller than epsilon prime plus something which does go to 0 as n goes to infinity. And that was, that was for every epsilon prime. So for every epsilon prime, there exists a capital M, then you use this capital M, then you send little m to infinity. And because this was true for every epsilon prime, then we have that the limit of this quantity is 0 as n goes to infinity, or in other words, as the mesh size of the partition goes to 0. And this concludes the proof. So this concludes the proof of the fact that whenever you have a process that is standard, so it's satisfied the, well, let's write it. Well, let's keep writing it as a stochastic differential equation. That's what we're going to be doing after, but you have to remember that this needs to be interpreted in an integral form. So dxt is a dt plus b d dt, with a almost surely in L1 and b in L2 log. And then b in L2 log. Then what you have is that the quadratic variation of this process is the integral of bs squared ds from 0 to t for all t in any finite time interval you might want to work on. Okay, that concludes chapter 5, and we now have all of the tools we need from calculus, all of the equivalent of the fundamental theorem of calculus, equivalent of the chain rule, the integration theory with appropriate Riemann sum approximation, all the tools we need to solve stochastic differential equations of a form that is more complicated even than that. So we're going to increase the class of processes we can study. We have all of this standard process for which we have a very strong form of calculus, a strong stochastic version of calculus. And now we're going to be able to look at stochastic process that we obtain as solution of equation involving these kinds of processes. That's the next chapter.